everybody. Today is the 9th of February, and we are beginning to talk about Chapter 3. The topic of Chapter 3 are properties of pure substances. So the first thing we want to do is to define what a pure substance is, and then work with that to develop an expression or way of looking at it in terms of its phase behavior and its state. So I'm going to go to the document cam, and first of all, we'll just talk about what is a pure substance. A pure substance is one that has a homogeneous or the same chemical composition throughout. So if you have a single substance, such as water, if you have liquid water, it's H2O. If you have gaseous water, it's also H2O. And therefore water, even if it's in two phases or three phases, the same thing works for ice, is a pure substance. There are other materials, some mixtures, that are only pure substances if they exist in a single phase. For example, we had talked about distilling alcohol. And if you have a liquid, you're fermenting a batch of something, it's water plus alcohol. But because alcohol has a lower boiling temperature than does water, this is going to have more water, less alcohol, and the steam, although it's still water and alcohol, you now have a higher concentration of alcohol, and there's less water in the steam. So in a finished product, it could be that if you have a fully fermented batch, you might have 14% alcohol by volume, which is called ABV. And after you distill it, you can get up to, well, it's 140 proof, so you can get up to maybe 70% alcohol or ABV. And so the quality or the composition of the steam is not the same as the composition of liquid. So the liquid would be a pure substance, and the steam would be a pure substance, but if they are taken together, it is not a pure substance. With water, steam, liquid, solid, it's all a pure substance. This becomes important because basically in this class, when we do our analysis, we have to rely on our substance being a pure substance. And if it's not, it's really the subject for a different, more involved study of thermodynamics, such as multi-component thermodynamics. So in here, what we're really doing is just sort of a litmus test. Is it a pure substance? Yes, we can do the problem. No, we can't. So all the problems I'll give you on the test will be pure substances. Yes, so the phase, when we talk about this, then that leads us into this idea of phase. And in general, the three phases we are most comfortable with are liquid, solid, and gas, or vapor. There are also some others, such as a plasma, some certain types of supercritical fluids. But in general, in this class, when we talk about phase, we'll be talking about solids, liquids, and gases. Sometimes there will be more than one solid phase of a material, more than one gaseous phase of the material, more than one liquid phase of the material. Water, which is our go-to substance for many reasons. One is because it's just everywhere, it's so common, or the word I would choose would be ubiquitous, which just means everywhere. Water is ubiquitous, and we use it for everything. So we analyze water quite a bit. Another substance that we're very interested in is refrigerant, R134A. Refrigerants, by their nature, have very specific phase behaviors. They flash from liquid to steam and then condense from steam to liquid at very tight ranges of pressure and temperature, and that's by design because that's what we want them to do. And later in the semester we'll talk about the process of refrigeration, which is really an interesting process that always requires a refrigerant of some sort. And R134A is the standard refrigerant that's being used in the United States right now. Up until 1993, the standard refrigerant was R12, and prior to that, they used something called R40, which was a different kind of a refrigerant. They all have good points and bad points. R134A was previously considered to be dangerous because it's quite flammable. However, R12 was damaging to the environment because it affects the ratio of oxygen to ozone in certain conditions. And so it was throwing off, or they believe it was throwing off the balance of ozone in the atmosphere, which was creating temperature change or climate change. So we no longer use R12, we use R134A. Mentioned last time, ammonia is also a really great refrigerant, but it's also extremely toxic. So it's not good for putting in your kitchen or in your car. Right. One of the most interesting things in terms of thermodynamics is this idea of a phase change. And what a phase change is how a fluid, and when we talk about fluid, we mean liquid, gas, or a combination of the two, or some combination of those ideas, how a fluid moves from one phase to the other, moves from one to the other. And every fluid is somewhat unique in the sense that where the phase changes occur in terms of pressure and temperature tend to be different, and they tend to be a fingerprint of the substance. So since we talk about water all the time, I wanted to put up a diagram, a three-phase diagram of water, showing ice, which is solid, water, which is liquid, vapor, which is gas, and we also see the critical point and the triple point here. The triple point is where all three of those phases coexist. Each of these lines are boundaries between phases. So ice to water is the boundary between liquid and solid. Water to vapor is the boundary between liquid and vapor. And down here where we have the boundary between vapor and solid is called sublimation. So if you look at your scales, we have pressure and temperature. There are many sets of pressure and temperature conditions where we sublimate, many sets of conditions, pressure and temperature, where we either melt or evaporate, or condense or evaporate, and many sets of conditions where we melt or freeze. However, there is a single temperature pressure combination at which all three of these phases for water exist at the same point, and that is at 0.01 degrees centigrade, which is just below freezing, but it's at 0.006 atmospheres, which is an extremely low pressure. So we really have to pull that with a vacuum pump in a laboratory. That's why we don't see water sublimating in everyday life. The critical point is a point above which, when I say point, I mean a pressure and temperature, above which there's no clear demarcation between liquid and vapor. In other words, we don't see a big change in specific volume or a big change in specific properties of any sort above the critical point. Now, all of these areas are really interesting, but in thermodynamics, this is sort of where we focus for all sorts of different fluids. We focus on the phase between water vapor and liquid water. And we look at how energy is different as we cross that boundary and what goes on as we cross that boundary. So the next part of the lecture, I'm going to take that curve, essentially turn it sideways, and take a look at water recognizing that this is going to be similar but happen at different conditions for other substances as well. In other words, this two-phase or phase behavior curve, you will have a similar curve for any sort of a liquid, vapor, fluid system. However, the one that we're looking at is kind of more particular to water. All right, so if we take temperature and we plot it against specific volume. Now, if you remember, specific volume is, generally speaking, it's 1 over the density. So in other words, density is measured in kilograms per cubic meters or slugs per cubic feet. So if V is the reciprocal, instead of being dimensions of mass per volume, it's going to be in dimensions of volume per mass. All right, so in other words, we're looking at how expanded things are. The larger the specific volume, the more room it takes up. So if you have a very light gas, it's going to have a smaller specific volume than a denser liquid. Well, it turns out that if you plot these things, if you have a liquid water and you transition to a vapor water, if you proceed isobarically, isobarically means we stay at the same temperature, same pressure. So perhaps we're at 1 atmosphere of pressure. If we're in the liquid phase, and if we expand, or we can add heat to it, is really what's happening. We watch the specific volume expand and the temperature increase until, very slightly really, until we evolve the first bubble of a gas. And during the time that the water vaporizes from the first bubble to 100% bubbles, in other words, we're going from a 0 quality steam to a 100% quality steam, the temperature will remain the same as the specific volume increases and as the pressure remains the same. So after we reach 100% vaporization, we then proceed to increase the temperature again. And this area, this is kind of an old-fashioned term borrowed from chemistry, but it's called a superheated steam. And the reason that they refer to it as superheated is it has more heat than it needs to be 100% vapor. Over here, we call liquid that is not on the verge of becoming a gas, we call it a compressed liquid. And inside, between here and here, we have two-phase. So in other words, we have some liquid and some vapor coexisting at the same temperature and pressure. For us, for water, if we were at 1 atmosphere of pressure, on my isobaric expansion line, we would also be at 100 degrees centigrade. And between those 2 points, the water will boil, temperature will not increase until the last little bubble of gas, the last little droplet of liquid evolves into a bubble of gas, at which point the temperature will increase as well. Now we also know, since this is our boiling temperature, that as we increase our pressure, if this were, say, 1 atmosphere, if we increased it to 2 atmospheres or 3 atmospheres, we would also increase our the temperature at which the boiling occurs. And if we then connect the dots between this point where the first bubble of gas evolves and the last bubble of gas evolves, we have an envelope showing the conditions of specific volume and temperature under which we are two-phase. And over here we have these the temperature-specific volume combinations at which we are compressed liquid, and over here we have vapor. Now, at the point where these two curves meet, This is called the critical point, and the critical point is that condition above which we don't have this clear demarcation. In other words, an addition of heat does not show a marked increase of specific volume. It just looks smooth above that case. So compressed liquid, superheated steam, and in between we have something called a two-phase in the envelope. We have gas, vapor, and liquid coexisting, and pressure and temperature are not independent. In other words, everywhere in here, temperature, pressure is the same. Obviously, it's denser here, less dense here, right? There's also more heat associated with water that's almost entirely steam than there is with water that's almost entirely liquid. So the properties as we cross the two-phase envelope are different, but pressure and temperature, we can't fix our state within the envelope based on pressure and temperature alone because they are not independent in the two-phase region. All right, so this line from here to here is referred to as the saturated liquid line. And once again, that's sort of an old-fashioned chemistry term. Saturated, if you think about like having a beaker full of water, you pour salt into it until the salt starts to precipitate out. Right before precipitation occurs, say that the liquid is saturated with salt. So what they're really saying here is at that point, the liquid is saturated with bubbles, and they're just ready to come out. So any change to it is going to precipitate out the bubbles. It's not really a totally accurate term. It's just the way that they refer to it. So over here, this is called the saturated vapor line, and they meet at the critical point. Now, there's sort of other colloquial terms. Sometimes the saturated liquid line is referred to as the bubble point, and the saturated vapor line is referred to as the dew point. And dew point is also a term that they use in weather. But basically what dew point means is you're just on the verge of having everything that's vaporized start to turn into liquid. And over here, you have everything that's liquid just on the verge of wanting to turn into a gas. All right, so in the two-phase envelope, which is also called the saturated fluid envelope, but I'm just going to call it two-phase envelope for now. We refer to something called steam quality. And this becomes a very important determination of independent variables within the two-phase envelope. Steam quality, which is designated by the letter X, okay, is not defined for a compressed liquid. It is not defined for a superheated steam, and it is not defined for a supercritical fluid. It is only defined when you have some liquid and some steam coexisting. It's an important point because when we start to fill out charts with this, which is going to be one of our exercises, X is not applicable. It's not 0 over here. It's not 100 over here. It's not applicable, not applicable. It only has a value within the two-phase envelope. So what is X? Steam quality, X, is the relative mass that exists in the vapor phase at a particular condition over the total mass. Or you can say the mass that exists in the vapor phase divided by the mass in the vapor phase plus the mass in the liquid phase. Okay? Now, they subscript these m sub g, which is the mass in the vapor or gas phase,
Mass in the vapor plus what?
mass in the liquid phase.
Oh.
And then they subscript that, and it's really kind of incorrect, but it's industry accepted in the industry, that you call m sub f, which is mass in the fluid phase, but I'm not going to write that down because fluid really means liquid plus vapor, but when they use like this term, they really mean liquid. Right? All right, so if we continue with this discussion, we also know that the total volume of our system is going to equal the volume in the gas phase plus the volume in the liquid phase. And we know that specific volume is equal to volume over mass. So we can say specific volume times mass is equal to volume total. And because of that, we could write this as being V of the gaseous phase times M that's in the gaseous phase plus V in the liquid phase, which we call V sub F, times M sub F. And that is going to equal V total, which is also going to be the total mass times the average specific volume. Okay. All right. Well, continuing with this line of thought, we know that mass total is equal to mass in the gaseous phase, or they call vapor, am I right, plus the mass in the liquid phase. So I can say, to simplify my variables, that the mass in the fluid phase, the mass in the liquid phase, is equal to the total mass minus the mass in the gaseous phase, like that. And so I can plug that into this equation. I get MT times V average equals, instead of writing V in the fluid phase, I'm going to just switch my terms here. I'm going to write V sub F times M sub T minus M sub G times V sub F plus M sub G times V sub F. Okay? And if I divide through by M sub T, I get V average is equal to MT minus MG V sub F over, this is quantity, MT plus MG V sub F over MT. Okay, and if I separate this out, I can see that this is going to be 1 minus M sub G over M sub T times V sub F, and this is going to be M sub G over MT times V sub F. And what we see then is that this is actually equal to X. So I can say, therefore, V sub average is equal to 1 minus X times V sub F minus X times V sub G. That should be a plus. Plus, plus, plus. There we go. And finally, if we solve for X, you can say that X is equal to V average minus V sub F over V sub G minus V sub F. And in the tabulations, V sub G minus V sub F is also listed as V sub FG. It's just the simple subtraction of those two variables. which has always seemed to me like the biggest waste of a column in the tabular data, but it's still there. And it can save you a little bit of trouble once in a while. And so this is an equation for calculating x. It turns out that you can use that idea for any physical property in the two-phase region. In other words, we make an assumption that across the two-phase region, all of our properties, little b, little u, little h, little s, are proportional or linear functions by mass in each phase. And so this is generalizable. This relationship,
Can you show that top one a little bit?
like that,
Oh, I guess I'm gonna switch fingers. Yeah.
okay, that better?
Yep.
Do you have enough?
Yes.
Okay, this relationship holds true for all physical properties in the two-phase region. And I should say all physical properties, all intensive. It would hold true for extensive properties, but the intensive properties are what we tabulate. In other words, internal energy average equals U sub F plus, that looks like a B, I want U, plus X times U sub FG, which is the difference between U sub G and U sub F. H sub average equals H sub F plus X times H sub FG. S average equals S sub F plus X times S sub FG. And because of this, we generalize to say that any physical property that is intensive is given the designation Y. So in other words, U could be Y, H could be Y, S could be Y. And we can then say that Y average, any physical property intensive in the two-phase region, is equal to the value of that physical property for the fluid, for the liquid, at that pressure and temperature, or pressure and specific volume, or whatever defines it, plus X, steam quality, times Y sub FG. Okay? And we will use this over and over and over again when we are working with thermodynamic problems. So we're going to learn it in Chapter 3, and then we are going to use it forever. So if you don't get it, you need to do your homework. You need to get used to it. It's not difficult, but it's a different way of thinking about tabular data. And so if you don't get it, you need to do all the homework, you need to practice, and then you need to make sure that you're clear on it, because it will not go away. Okay? So I'm going to write that on my notes so that it's on the video. This, it's not really a principle, but I would say it is a solution technique. Will be required throughout our class. So you must learn how to do it. Every now and then, I just get a student that hopes it goes away, and it never turns out well for those students. So I'm just warning you in advance. It's not that hard. It's just a different way of looking at things. So some people don't like to do it. Now, the other thing that they sometimes call this two-phase envelope, two-phase fluid, is what's within that envelope. is also sometimes called a saturated liquid vapor mixture. That just means that you have the two liquid and vapor coexisting in some quality of steam. Okay? And so, let me do a problem for you. Oh, there's one other thing I want to put on the notes. Tabulated data is empirically derived. Does anyone know what that means? Sorry? No? Okay.
No.
What that means is it is much more real or closer to real than values from equations. Therefore, if you ever have data, tabulated data, it is not okay to use an equation instead, because equations are approximations. What I mean by that, let's think about an equation of state that we have for relating these variables. The ideal gas equation, PV equals nRT. First thing, to use the ideal gas equation, what kind of a fluid do you have to be working with? It has to be a gas, right? It's ideal gas law. It's not ideal anything law. So it's completely invalid when you're talking about two-phase fluids or when you're talking about liquids. It just doesn't work. So it has to be a gas. Not all gases are ideal. Do you guys remember what makes a gas ideal? What sort of ideas go into that? Low pressure, high temperature, no molecular volume, no interaction between the molecules of the gas. So in other words, it's a fake gas to begin with. It has to be very simple, maybe monatomic. It has to be in a huge container, not compressed at all with maybe a vacuum pulled on it. And the molecules cannot want to attract or bounce off of each other or have any interactions whatsoever. So sometimes the ideal gas law may be your best bet. But once again, it's comforting to use the ideal gas law because you're very familiar with it and you're probably very good at using it. However, it's not acceptable if I'm asking you to use tabular data, okay? And that's not just me, that's thermodynamics. So I just want to really stress that because, once again, once in a while I have a student that really resists this idea. And it's not that the ideal gas law is bad, it's just that it's an approximation. So if you have real data, it's infinitely superior to an approximation, okay? All righty, so let's take a look at some sort of a problem and see what we can come up with. And this will go on for a long, long time. We're going to work on this for at least one more day. But I'm going to go to the homework set, or the homework problems, and I think I'm just going to jump into it, and I'm going to do problem 320. 320 is a partially complete table for water, and it asks us to fill in the other values. So we have 4 columns. We have temperature, pressure, internal energy, and phase description. Temperature, pressure, internal energy in kilograms per, or kilojoules per kilogram, and phase description. So the phase description is going to be whether it is a liquid or a mixture or a vapor. And we always have to go back to this idea of our two-phase diagram, okay? And I'll refer to that as we go forward. All right, the first one, we have a pressure of 400 kPa and an internal energy of 1,450 kilojoules per kilogram. Let's just start right there. All right, so we want to find the temperature and we want to find the phase description. We need to go back into the appendices of our textbook. We talked about this really briefly last time, but in Appendix A and in Appendix AE, which is Appendix 2, we have SI unit tables for water. We have SI unit tables for refrigerant, R134A, and then we also have English unit tables for both of those substances. So first of all, we see that we're dealing with water. And which set of units are we in? Are we in English or are we in SI? Yes. So we want to take a look at the proper tables, and those would be the tables for water for SI units. So this begins on page 904. And I'll show you what that looks like. Once again, my tables, I might have, I think I have these somewhere on my personal drive, so I'll see if I can, because they would project 1,000 times better. But we're looking at table A4, page 904. If you have yours out, you'll be able to read a lot better. But at the top, it says saturated water temperature table. Saturated water means these are the sets of conditions for the two-phase region. So the first thing that we want to determine is, at this pressure and this internal energy, are we in the two-phase region, are we a compressed liquid, or are we a superheated vapor? And the way that we do that is we find that pressure, which is, we would probably want to go to the pressure table. The first set of tables are based on temperature or organized by temperature. The second set are organized by pressure. So if I go to table A5 and I look at the pressure organized tables, I'll see that this column tells me that it's pressure in kPa, same units. So I go down to 400 and I take a look at my internal energy. If I go over to the columns for internal energy, what I find is that U sub F at that set of conditions is listed as 604.22, and U sub G is listed as 2553.1. All right, so the first thing is this value of U is greater than U sub F and less than U sub G. That means that we are in the two-phase envelope, or our phase description is two-phase or saturated vapor. Excuse me, saturated fluid. If my value of U sub G was, say, 5,000, that would mean that I had more internal energy than I needed to be in the two-phase region, so it would be superheated. So the first piece of information I have here is that this is two-phase or saturated fluid. That means that my temperature is going to have to be whatever the saturation temperature is for those conditions. So going back to table A5, at a pressure of 400 kPa, I see that my saturation temperature, or the temperature clear across that two-phase envelope, is 143.61 degrees centigrade. All right, so there's our first line of our first problem. Do you have any questions about that at this point? I was going to finish off this problem so that you'll have it, because you'll be doing some work like that. Okay, the next one is, I have a temperature of 220 degrees Celsius, and I'm told that it is a saturated vapor. All right. Now, what saturated vapor means is we're on this side of the curve. We have a steam quality of 100%, and that means that all of my properties are going to be the sub G property. In other words, this value. Because there's no amount of condensate or dew, we're at 100% steam quality. So my U value is 2553.1, but I'm still in that envelope. So whatever my pressure, saturation pressure is at 220. Oh wait, this isn't correct. I'm sorry, I was working at the wrong temperature. Sorry about that. Got carried away. So let's go back to the appendix. And this time we're for temperature. Sorry?
If it doesn't have like specifically two.
It does though. You have to go to table A4 because if you're in A5, it's organized by pressure. So AC, yeah, very nice. So if you go back to table A4 on page 905, you see that at a temperature of 220, the saturation pressure is 2319.6. 2319, sorry. 220, 2319.6, check units, kPa. Now my U is going to be U sub G at that pressure and temperature, which is 2601.3. Same units. Right? The third line says we are at a temperature of 190 and a pressure of 2500. Okay. If I look at, and I've completely torn up my book, which was not my smartest move, but there you go. If we look at a temperature of 190 degrees, which is page 904, we see that my saturation pressure is only 1255. So is the pressure of this state higher or lower? It's higher, isn't it? So what does that mean? That means I'm going to be over here. It's going to be compressed liquid water, isn't it? Because there's too much pressure. If you took a gas or something that was ready to become a gas, put more pressure on it, it would become a compressed liquid. Now, here is an interesting fact. The value that we can use here, we can use U sub F at 190 degrees Fahrenheit. Okay, because internal energy and thermodynamic properties in general are very strong functions of temperature. If we went into the table and used U sub F at 2500 kPa, the temperature would be quite a bit different and the value would not be as good. But if we stay at this temperature of 190 and we use the U value at the very bottom end of the two-phase envelope, it's going to be pretty good. Yep.
Should that be Celsius or Fahrenheit?
Yeah. Thank you. So 190 U sub F is 806. Same units. Okay. And then last but not least, we're not given a temperature. We have a pressure of 4,000 kPa. And we're told that the internal energy is 3040 units are the same. So since I'm given pressure, I want to start by looking at that saturated table for organized by pressure. So that's going to be table A5. And I'll see that at a pressure of 4,000, my saturation, or excuse me, my U values, the U sub F is 1,082, and the U sub G is 2,600. So this value is higher, isn't it? So what phase does that mean I'm in? I have too much internal energy to be a two-phase. So what's it going to be? Superheated steam, isn't it? But what is the temperature? All right. The way that we do that is table A6 has superheated water, which is what we need. And every little tablet, there's 9 little tablets, are all organized by pressure. So we go to our pressure of 4,000 kPa, which is 4 MPa. You need to look at the units because some of these are in MPa rather than kPa. Right? So I continue to right here, table A6, page 910. My pressure here is 4 MPa. So I slide down here. Do I have a temperature of 190? I really don't, do I? What does that mean? Well, that means that we're just right on the edge. We're just right in that 2-phase envelope. So we're somewhere in between. Our first point would have a temperature of 275 Celsius. Our saturation temperature is 250. So we're somewhere in between here and here. The best bet when that happens, oh, I don't even need my temperature, do I? No, this is my above. There we go. That's better. Now I'm getting better. All right, pressure 4,000, U 3040, so we forget everything I just said. So if I look at my numbers, 3040 is right in between 400 and 450, isn't it, in values of U. So in other words, pick off the value of U, see what temperature that corresponds to. It's 3040. I was reading 3004. It's in between 450 and 500, isn't it? It's not quite half. It's a little closer to 450, right? Now, we could interpolate, meaning we could set up a ratio, and we could say 400 or 450 minus the temperature over 450 minus 400. In other words, we're assuming a linear relationship. Then we would take our high U value, which would be 3100, minus our U value, which is 3040, and then put it over the entire span, the 3100 minus 3011. Okay, and we could solve this proportion for T. Now, this would be the most accurate way to do it. However, we can also see that it's approximately, if you look at those values, there's a span of 90 kilojoules per kilogram, and we're about 30 from the bottom, so it's about a third of the way between these, isn't it? So estimating it to be 460 or 465 would be a good estimate. I'll say 465. All right? So do you guys have any questions? That was a lot of information. We covered lots and lots of stuff today. The best way to learn how to do these, I will assign some of these tabular problems for you. The best way to learn how to do them is to do them. I mean, that sounds redundant, but it's just absolutely the truth. So what I'm going to do for your homework, and I will post this up to Moodle, I'm going to give you some of these to work with. I did 320. I want you to do 323, 324E, and those are both for water. Then I want you to do 326 and 327E, which are for refrigerant. So the process is exactly the same. Now, you'll also see that you have an equation solver, and 321 asks you to use the equation solver. We don't get to use the equation solver in here. And the reason is you don't learn where you are in terms of phase behavior using the equation solver. So you're not going to be allowed to use it on a test. If you use it on your homework, you'll be a sorry person. So I would recommend against using it. If you were out in real life and you understood where your flash points were and where things were changing, and you needed to get answers, and you didn't have your tables, I would use the software. But in here, it's old school. So, all right, thanks, guys. Have a wonderful day. And, I will not be in my office tomorrow or Monday, but if you need to get a hold of me, please send me a text or an email, and I'll get back to you ASAP. Have a great day.